Okay, well, we've reached the last coordinate system that we're studying to analyze curvilinear motion, general motion through space. And just remember, these coordinate systems are choices that we make for convenience to describe the motion under certain, geometrical constraints on the system, essentially. So polar and cylindrical coordinates are going to be convenient for describing motion in these central force systems where there's a central point and a force. I don't know, there's not a central point, there's just a force that's always pulling and then keeping something in a maybe some sort of a circular orbit, like a ball on a string, car driving around a curve, all these things that have some sort of natural circular tendency to them caused by the central force. And in that sense, it feels a lot like the way we looked at the natural coordinates and how those were introduced. But this is different, all right? But as I've talked about in the past, like the choice of a coordinate system is just that. It's a choice for convenience. All of them, you should be able to describe general motion in them. It's just the choice of a coordinate system may make that description, that kinematics analysis, the geometry of the motion, a bit more straightforward, or maybe even sometimes it's better to say it makes it a bit more telling, right? But this is the last, so we've talked about Cartesian. Well, so first we started with rectilinear motion, but now we've talked, that's just motion in a straight line. Don't really need a coordinate system for that, it's just a one-dimensional line. We have then Cartesian, natural, and now polar coordinates. And this is where we're gonna leave it and move on after this. But this should be hopefully a bit of a shorter video. We'll just talk about the theory here, and then the next video we'll come back and do some examples. Okay, so polar coordinates. Now we'll start with the Cartesian coordinate system on here, just for reference, just because we have, I don't know, more experience. Hopefully that feels a little bit more intuitive because, so we just kind of put it on there. Let's put a path that a particle is taking, okay, and go somewhere on that path. And let's purposely put it not, like here would be kind of misleading. So I'm going to put it like on a downslope portion here. What I mean by that is this would be fine, it's just the vectors we would draw wouldn't be so exactly clear. Okay, there is our position vector, and as we did previously, we have an angle from the horizontal. Okay, this is point P, and let's put it right here. Okay, all right, so now let's okay, let's have a reference here. The natural, and so we'll put all three coordinate systems. So here is our I, and here is our J unit vectors, right, along the X and Y coordinates. Now, it would make more sense to kind of pull that up and put it right on the point, just because that's to put a perspective. Remember, these are vectors that can kind of float around anywhere. It's just their direction that matters. Let's also put in just for reference, the natural coordinates, which are tangential, AT, and then normal. Okay, and I think this is looking good. We'll be able to fit our polar coordinates on there, right? So I put these on here first just to highlight the difference in the polar coordinates, right? So this, no matter what, tangential and normal always, and for all of them there, if we extended this down, there would be right angles here between the two base vectors here. Our polar coordinates are going to be different from these, even though they might feel like we're doing the same thing, okay? The way we define our polar coordinates is continue in the direction of the position a unit length. So the direction here is going to be the direction, the radial direction, and then perpendicular to that in the positive change in theta. So that would be, if theta is defined from the horizontal axis, we actually have to go back here. There is your other coordinate, Okay, so this has really nothing to do with the tangent to the path or the velocity vector. This has to do with its position at that current point, right? And that's how this is defined. And so again, to me, I think the natural coordinates are the hardest ones to kind of visualize. Polar coordinates make more sense because we're one step down on the motion, right? It's just its position from the origin, right? And that gives you the direction of the radial direction. So any unit vector, all you're really doing there is specifying a direction. And then we have an angular unit vector, right, related to the angle theta. And this is perpendicular to ER, as all of our base vectors are for our different coordinate systems. And it's in the direction of increasing theta. And so because of the definition of theta from the horizontal in a counterclockwise way, we actually have to go against the direction here. It would be the positive E hat theta. Note here, too, we could just say the same thing here. This is in the direction of increasing scalar distance r, right? So that's the actual magnitude. So if we go out to a higher radius, that would be the direction of E hat r, right? And only that direction, right? So if we go up the path, we're going to have components in each. To move the particle in the E hat r, we would just go to a higher radius without changing theta. And that's why in polar coordinates, r and theta are the the important, or are the coordinates. Okay, and then we'll put this down in writing here. This is different than natural coordinates, or our normal tangential coordinates. Okay, and showed that here by putting them both, actually all three of them, right, on one plot. Okay, great. So now let's describe the motion. To do that, we first have to write out the position. Okay, and so this now gets into the increasing r I had up here, right? So that position vector is totally described by, and this is like the advantage of this, right? A scalar distance from the origin and the direction, right? Breaking down that into two different parts, just like we did with the natural, except for our natural coordinates, the easy thing was the velocity. We said the velocity vector was just the speed times E hat t, or the tangential direction, right? This now in polar coordinates, right? It's the position vector that's just trivial. It's just distance from the origin to point P, right? And that gives you the magnitude of the position vector, and then E hat r is the direction, which yeah. Okay, so that really incorporates, what our theta is here. Okay, so now that we have the position vector, again, that's just the one that comes easy in the polar coordinates. And by the way, polar and cylindrical coordinates, all we have to do, and we will do this near the end here, at the very end here, is add a third dimension. So this is the 2D. And if we go 3D, we keep this polar coordinates in the plane here, and we add another dimension, which is just a z coming out into the page, and that acts like a Cartesian extra coordinate direction into and out of the page. So we're going to just be in polar coordinates, and then at the end trivially add the z direction, essentially. Okay, back to this, right? So we have our position vector, v. This is now general. This is just always true, dr dt. Now let's plug in our form for our position vector. Okay, this is then dr dt E hat r. And now be careful, think, right? As we move along, as the position vector changes, right? So let's go along the path, right? So as our position vector changes in time, right? That maybe use the pen would be better than my finger, right? As the position vector changes, and we try to stay on the path, the direction my pen is pointing is changing, right? So in time, our unit vectors rotate, and luckily we've already worked through generally. But so we have to do the product rule here, meaning that we do need to include this term that in Cartesian we just like throw out, because I hat and j hat don't ever change. No matter where you are, you just kind of translate this I hat, j hat things around. So you take the I hat, j hat, put it on the point, and as it moves, it stays there, but the actual I hat doesn't change. It's always pointing to the right, and j hat's always pointing up. That's not true for these other coordinate systems. Okay? So we've now seen, we derived this, and then we've used it once before. So our change in these unit vectors through a rotation is going to be the change in theta in time times the normal vector to the, so this is the normal unit vector to the vector that we're taking the derivative of. Okay, so this is, well, that's it. But just remember, the reason it's e hat theta is that this needs to be normal to e hat r. Okay. Okay, great. We might make a further statement on that here in a second. Okay, so our final result is that V is equal to r dot, which is dr dt, with the radial unit vector plus r omega, all right, r, and then d er dt is omega e theta, or our unit vector in the angular direction. And that's it. That's a nice form. All right, so now we've written this in terms of the two components, and we have basically a radial velocity and this r omega term, which we know to be the velocity, the tangential velocity at some distance r here. So we have the looks like a tangential velocity, but in a circular manner, right? So that's the, if you were in a circle of radius r, what your velocity would be, and then we have a radial velocity as well, right? So that should be able to reason through those. Okay. Now on to acceleration. Our acceleration is change in velocity with time. Plug in what we just found for velocity. Take a derivative. Okay. This one, right, is going to be a little bit more steps. So maybe give myself some more space down here. We're going to have basically, so we have two terms in summation that each have, oh, not each, I'm sorry. So there's going to be a product rule here, which will be 2 terms, and then we'll have a product rule here, which is actually going to be 3 terms. We should have 5 total terms, right? So we have, the first one is the r dot gets another derivative, and then nothing applied to e hat r. We then have r dot d hat er dt, right? So that's the product rule for that first term. And now we jump to the product rule for the second term, right? Derivative of the first, keep the others the same. Derivative of the middle, omega dot, keep the others the same. And then derivative of the last. And that's the nice expansion. Now, this is where I said we might need to make one more statement about what I set up here. Because the things we don't know here, we don't know what to do with this, essentially, right? We have tools, everything else. So we know that this, we just derived it here, is omega, or we could write it as theta dot. And then in the angular unit vector direction, right? So we have all that, and we can then combine all these, but we need to know what this is. Okay, so there's just one like little nuance here. When I said normal to e hat r, that's fine. It's actually what we're looking for. This property, this identity, works. So you take the derivative of a rotating. So in a rotating reference frame. Right, so as we move along here, the e hat r e theta is going to rotate kind of that way. Right? And this identity works by saying, well, the change in the unit vector through time is given by the omega, the angular velocity, multiplied by the unit vector that is a 90-degree rotation from the original. Okay, so actually, e hat theta is a 90-degree rotation from E hat r. And that's why we were able to just say this, right? Okay, so when we come down here and extending this idea for E hat theta, we need to put in negative E hat r is 90-degree rotation. So all of this extra discussion is all about that little negative sign there. That's just what the identity is, right? So as the system rotates, so as we flow down here in the system, the coordinate system kind of goes like that. All right, as we move along, I'm trying to keep this always pointing to the origin. All right, as we do that, we want to know how E hat theta is changing in time, and that's going to come from a negative 90-degree rotation of the E hat theta itself, which is minus E hat r. Okay, but other than that, everything stays the same. So this then will be replaced with a minus theta dot E hat r. Okay, so that won't go away. Let's just sneak it there at the top. And let's see if we can get to a final result here. All right, it's getting a bit lengthy here. These accelerations do that. Okay, so we look now, what are the terms that are in the rate with the radial unit vector? It's this first term and the last term. Okay, we have an r double dot and a r omega theta dot. We can simplify that in a second in the next step. And then we're going to combine the angular unit vector terms. So we have an r dot theta dot from this term. We have a r dot omega from that term, and we have an r omega dot from that term. Okay, so now we just make the notice that the change in theta with time is the angular velocity, and the change in angular velocity is the angular acceleration. So this is going to be r double dot r omega squared, because theta dot is just another omega, yep, so I'm actually pulling this term to the front, r omega, I'm just trying to match the form that we see in the book, r alpha from that term, and then these two terms are the exact same. These are both r dots times omega, right, because this is theta dot is omega. So 2r dot omega E hat theta. And that's the form we're looking for. So this is the acceleration written in terms of the radial distance from the origin to point P and any angular velocity and angular acceleration. This is then our radial component of acceleration, and this is our angular component of acceleration. Let's put a big box around this. This is important. Okay, so let's spend a little bit of time talking about each of these individual terms. Now because of that, those two turn out to be the exact same thing. We actually only have 4 terms to discuss here, and 2 in each part, right? So what causes radial acceleration? Now when we work through these terms, and some of these are just going to be new vocab, right? We won't be able to talk about these things physically without talking about the forces. What we're actually talking about is a point P is right here. What are the different ways the kinematics can cause an acceleration radially? So from this point, what would cause an acceleration further from the origin or directly towards the origin versus just kind of moving in by changing the angle? So that would be like movement in a circular direction. Yeah? Okay. And we kind of did the same thing when we talked about what could cause something to move in a tangential versus a normal direction, right? We're doing something different here, which is to say, well, it's at this point, what would cause it to push itself further away from the origin, or come in, and then or just stay in a perfect circle, E hat theta. Or not stay in a perfect circle, but accelerate in that perfect circle. Okay? So these are the two contributions to that radial acceleration, pushing or accelerating away from the origin or towards the origin exactly. Well, r double dot is directly radial acceleration. Right? That's the actual change in that distance. It's the second derivative of the distance from the origin to the point P. But we also have this other term, minus r omega squared. This is what we call centripetal acceleration. Okay, so this is a if there's some sort of angular velocity here, we get a centripetal acceleration. Okay, the two terms over here on the angular side, we have an r alpha. This is tangential acceleration. Directly, right? Just meaning that when a point has a angular acceleration, this is then the translational acceleration associated with that at a particular radius. And then we have one other term. This one is called the Coriolis acceleration. Okay, and when we get to the examples, we'll talk more about the individual components here. Okay, but before we do examples, which is not too far away, I mean, it'll be in the next video here. But let's go back to this special case, which is just purely circular motion. So we already did this for natural coordinates, our normal tangential. So let's see now again, what's the proper choice? What's the most convenient choice for coordinate systems to do analysis? That is not a set thing. You can do it in natural. Sometimes it's desired to do it in polar. And so the same exact system that we've looked at with natural coordinates, we can do it again in polar. Okay, so let's 1, 2, 3, 1, 2, 3, 1, 2, 3. So something is causing the system, some force is causing the system to stay in a perfect circle. It's a pretty good circle, I'll tell you. Let's see here. Let's say motion is that way, and so our omega is theta dot. What is theta? Well, theta would be, let's go out to the point there as the point we will analyze. So our theta is right there, and these are all functions of time. We have to put a radius. So because we're in circular motion, that radius is always a constant. So this, whenever we see like little r here in our equations, those are functions of time that are the magnitude of the position vector for the particle from the origin, right? And here I guess the origin is right there in the center. But in a circular motion, that little r is always just this constant big R. Okay. So at our point, let's do it this way. We have, so this is our position vector at this time, right? The magnitude of that is always r, but that's direction part of the vector always is changing. All right, so at this instant, ER is there, and E theta is normal to it, in the direction of positive theta change, so more counterclockwise rotation. Okay, I think that's everything we need in the picture. So little r is always big R, which is a constant. Therefore, r dot is 0, and therefore r double dot is 0. And a lot of these are going to then cancel, right? This first term is going to not cancel; it's going to be 0. This last term is going to be 0. So we'll have no radial acceleration. Does that make sense, right? Well, of course. I mean, there's no direct radial acceleration because we don't see any change in our radius. We're staying at the same exact radius. We also don't have any of this Coriolis acceleration. Okay, so our velocity then is r omega e hat theta. That, okay, so let's go remind, where did that come from? Right, here's our velocity that we have already written down, this first term is 0, right? There's no velocity in the radial direction. There's no velocity component that's pointing out. Everything is purely in the theta direction. Our velocity vector is purely along e hat theta. And then our acceleration minus r omega squared e hat r plus r alpha e hat theta. Okay. All right. So that's it. So in scenarios where we can say, well, the kinematics here, the actual geometry of the motion is a pure circle, we can jump to here. But only in that case, right? If there is some deviation from circular motion. Now, it doesn't need to be like constant omega, right? Omega can change in time. If omega is changing in time, we have an acceleration, angular acceleration that goes into here. But if the particle stays in the circular path, we can jump to here, which is a simple, a special case of the velocity and acceleration vectors that we have above. All right, so last thing before we wrap this up is, well, everything so far has been polar coordinates. Cylindrical coordinates is just a 3D extension. So we have polar coordinates in a plane. So typically we associate, like, this is just the way we think about it, is like the XY plane. And then we add one additional Cartesian, so this would be the z-axis, and it will have a k hat base unit vector. And that's it. I mean, so all we're going to do is take our three definitions for position, velocity, and acceleration, and we will just have, well, this was r e hat r, r dot e hat r plus r omega e hat theta, r double dot minus r omega squared e hat r plus r alpha plus 2 r dot omega e hat theta. And at that point, I'm just going to try to do this really lightly. This is polar coordinates. Okay, now we add on plus the z coordinate in the k hat direction plus the z dot k hat plus z double dot k hat. All right, so this is like with that added dimension, and all we're saying there as well, if we allow motion to come in and out of the page, so the path kind of sweeps through this but is also kind of tilted upward, right? Then there could be, you know, it's just a way to describe the motion, just a way to express it, that we want to allow for velocity coming out of the page, and we want acceleration coming out of the page as well, with this position in the out of the page direction. Okay, and that's the whole thing is cylindrical. All right. Okay, so we'll come back with just a couple examples in the next lecture.